Okay, good afternoon, 61C. You made it all the way to the end. The last lecture. Congratulations. So, the good news is today I'm not going to teach you more material. Everything that's going to be exam you've seen already. So, all I'm going to do today is give you an overview of everything we've covered in the class this semester. And it's pretty amazing how much stuff we've managed to get through. Basically the whole computer architecture stack. So one thing is about this new 61C we started doing a few years ago. It's not old school computers, it's things like personal mobile devices and warehouse scale computers, like the biggest and the smallest computers around. All the ideas that we told you are applicable to all these systems. And if you peer inside these warehouses, this is what they kind of look like. Looks like something off the Matrix or the Borg. And the old style machine structure is really about one system, this one little stack. But as you've seen this semester, we're dealing with way more complicated systems, massive parallel systems, all the way. We told you about those systems all the way down to individual transistors and gates. One thing to get across: it's not about C programming. This class wasn't meant to be a C programming class, though many of you learned C for the first time in this class. The reason we use C is just to get you closer to that hardware-software interface, which is what the class is about. How does software talk to hardware? That's why we use C in the class. But we really want to focus on these great ideas in computer architecture. What are the things that you should take away and think about when you're building any kind of system, not just a hardware system? Designing for Moore's Law. Technology continues to improve at a fantastic rate. It may be slowing down a bit, but it's going to improve in some other dimension. So make sure you design for trends. Abstraction to simplify design. That's a big key idea in computer science. It's the only way to manage this complexity is through abstraction. Making the common case fast. Focus on what people do all the time. Dependability. We talked about that. Memory hierarchy. Performance via parallelism, pipelining. Right. So what we're going to do now is go a power of 10 inspired overview. How many of you have seen the power of 10 video? Like an old, right? Okay, some of you. So let's start from planet Earth. It's kind of big, say 10 to the 7 meters around. We're now going to zoom in at all the different scales of computers we've been looking at in the class. So let's move in a little bit closer to some piece of a map. And this bend in the river in Oregon, what's there? Well, peer down a little bit, take the satellite view. Oh, interesting big set of buildings. What's this? Well, it's a warehouse scale computer. It's Google's installation, right? So you can go poke around in, I don't know if Google actually blanks out their own sites, but look in satellite imagery, you can find their data centers. And they try to keep these private because they don't want anybody just walking in and stealing drives from one of these things, right? Disk drive. So good look at the place. This is a view. So, it's sort of kilometer scale enterprise. Sort of peer down into one of the buildings. And one of the things when you see a data center, you'll see these massive cooling towers on top. The heat density in these things is amazing. They're burning, several megawatts inside this building, and they have to get that heat out somehow. So they have these massive cooling towers on top. So let's take a look at details of a Google warehouse. This data is a little bit old, but some of these centers are probably still running. So, roughly 100 meters by 100 meters, give or take. And in there you have 10 megawatts of power consumption. So 10 megawatts is a reasonable sized power station, right, to fuel that. 40,000 servers, couple 100,000 disks. These days the PUE may have gone down a bit, but in those days like 1.23. So what that meant was, of all the power you fed into there, 23% was just lost. The one is what goes to the actual IT equipment. 23% is what gets lost. About 85% of that is cooling, the power to drive the cooling. About 15% of that overhead is lost in the conversion. So you go from high voltage AC, you convert it down, you lose a bit of power, and you do that. Convert it down again to get to, say, 120 volts to get to the server. Then you convert it down again to get to the 1 volts that the chips run on, and you lose some more power there. So, but most of it goes into the power to drive the cooling. A little bit is lost in the power conversion as you step down. So the way Google built these warehouses, they actually, inside the big warehouse, they have another module which is a container. So a while ago, guys at Sun came up with this idea of why don't we put computers inside shipping containers? Like when people are building a big data center, they order a whole bunch of servers from them. We pack them all up, put them in a shipping container, ship it to them. They unpack it all and put it in another box, which is called a building. why don't we just build the computers into the shipping container and never take them in and out? You just build them inside the container. And it turned out, they had a business doing this, and outside Soda Hall, there used to be a container that the new building has wiped out, but there used to be a shipping container there that held the servers for Soda Hall. But Google apparently were doing this as well, but secretly. They actually have, in this warehouse, there are 30 of these containers stacked too high, and a few just stacked single high. So what does that look like? Looks like this. You go down to Oakland docks, you see something that looks like this, except it's probably full of iPhones or something. Here, this is full of big computers, and actually working computers. If you walk inside one of these guys, you look inside, what you're going to see is here's the management console, and here's all the racks. So the idea is just build everything in there, and you can just ship the whole lot around en masse inside the whole container. So the way that the heat flows in these guys, they have the hot air comes out here, is then pushed down, funneled through back to the cooling engines, which then push cool air in here. So you're recirculating the heat this way. The cold air is coming in, picking up heat as it goes through the servers, and you pull the hot air back out again and cool it. So here's the internals. They're just big enough for somebody to get in the middle of, and the cooling air is down at the bottom there. So inside the container, right, that's the next level of box. Inside the container, you have these racks. Right, and what do the racks hold? They hold lots and lots and lots of servers. So classic design is a 1U server. A U is a rack unit. It's 1 3/4 inches. It's an old standard from telecom days. So they pack servers in this 1U high, and they put up to 40 or so of these in a single rack. And what they do is they put so these are individual servers racked up, and then in the middle they have a big Ethernet switch that connects all servers together. So you have cables from all those servers going to the middle of the switch. It's actually called a top-of-rack switch, even though it's in the middle of the rack. Right? Whenever you draw the diagram, you draw at the top, but physically it sits in the middle. And it sits in the middle to keep the cables short, right? So cables feed into the middle. Then what's called an array, or sometimes a cluster, is a set of these racks, and these would all live together in one container. And then you have connections from the center of each of these racks up to a cluster level switch, right? And often there's a lot more bandwidth up and down. These guys can talk to each other much faster than they can talk across the cluster and back out again, right? So this is the next level down. So here's a Google rack for servers. One thing is, Google started building their own computers. They got tired of buying, computers from Dell or whatever, and so you'd have 100,000 CD-ROM drives, not really very useful in a data center, or 100,000, audio outputs. Nobody's really going to listen to 100,000 servers playing music, right? So all those are redundant components. They started building their own motherboards. They just threw away all the stuff they didn't need and just focused on the compute they needed inside the data center. And they didn't even bother with a box. When you have a box on your board, just put the bare board on a shelf in the rack. It just gets in the way of the cooling air. So here's one of the Google racks. They just use these bare boards in these racks. This is industrial scale computing, right? So talked about the hardware scaling down. How do you program at this scale? You guys already seen this you're seeing this now in the project, last project. Programming, you can program this whole array of machines just with a few lines of Python code, right? So this is really the power of abstraction. Just focus on the key things you're doing. In this case, a map reduce. And, with a few lines of code, you can make thousands of these machines, burst into life and do some useful computation, right? So just stopping here and looking at these great ideas and how they apply here. So designing for Moore's Law, you get more and more stuff every day. So designing these hierarchy of containers to contain everything. You have the warehouse scale computer, the container, the rack. Dependability, you have multiple warehouse scale computers. Google has, a few dozens of these data centers around the globe. They can shift capacity around between them. Inside each data center, there's many racks. One of them fails, that's okay. You just work on the other ones. And all those connections, there's not just one Ethernet cable to every server, there's at least two. And there's multiple paths through each switch for all the connectivity. So if a switch dies, it's okay. Things are still connected. So there's massive redundancy inside these computers. And then parallelism at the massive scale. You have this task level parallelism, request level parallelism, data level parallelism. You're exploiting across all these servers in a data center. And if you peer inside, let's look inside one of the servers inside these racks. So this is the motherboard of the... one thing to notice, again, this doesn't have a case. They just put the bare board in the rack, right? It's cheaper, easier to cool, easier to service. Why bother with a box, right? So just sitting there on the shelf. The disk drive is just exposed, a couple of disk drives. One of the cool things, when these pictures first appeared, people had a big shock, was every server had like a car battery next to it, right? So sitting next to it. So here's a battery next to the server. So why was Google putting a battery next to every server, right? These weren't laptops. These are inside these massive data centers. And data centers have amazing power backups, right? Because they're 10 megawatt installations. They have to keep running, even if there's a power outage. So where do you get 10 megawatts of power from when the lights go out, when the mains goes out? Well, it turns out that these big data centers, what they actually have is several cascades of backup. So they have batteries for a very short period of time, and then they have massive diesel generators. And these things are, about the length from here to that wall. Big things about this around. And, each one can generate a couple megawatts of power. And the thing is, though, when the lights go out, it takes a while for the generator to kick on. It takes, a minute or two for that generator to get running and producing power. And they need batteries in the meantime so the batteries just need to last long enough for the diesel generator to get going, right, to fill in the power supply. So that's one reason to have the battery, right? So you can run these things for a little while until the generator kicks in. But the other reason is pretty interesting. Let's just look at the details. So this one, they have a battery on the board. And one reason they did this was more efficient to have a battery on every system than to have big battery banks and then wire the battery banks to the boards. They'd lose power in just energy, the conversion, and the wiring and the conversion of that higher voltage from a central battery pack instead of having one on each server. These guys have a couple of disk drives. These are a bit older, 1 terabyte disk drives. These designs actually used AMD Opteron microprocessors. They didn't use Intel. And why is that, do you think? You hobbyists out there who build systems, why would you choose AMD over Intel? What's about the only reason? Cheaper, right. So when you're buying 100,000, it kind of matters how much each one costs. So these guys are very sensitive to, cost performance, right? Because they don't care so much about how fast each one goes. They can be buying a lot of them. They just care about the overall throughput on their task because they can use massive amounts of parallelism. So all they care about is the raw performance per dollar of the chips they're buying. And in this particular server design, they picked AMD parts. So this one has 8 gigs on board and a gigabit second Ethernet interface. I was going to say about the battery. One other thing they do with the battery, I can't remember if I mentioned this later, is I don't know how many of you actually pay utility bills, but there's a different rate for different power consumptions, right? So if you're at the lowest tier, you get charged the least amount of dollars per kilowatt hour. And as you go up the tiers, as you use more power, you charge more. At the industrial scale, they have these contracts with a power company that if you're using 20 megawatts, it's a real problem if you start using 21 megawatts, right? That's not a small blip. That's a lot. That's a big difference. And so the utility companies have these very steep, curves that you really don't want to use more than 20. If you say using 20, you want to only use 20. The problem is if all of a sudden, Britney Spears gets hot for some reason, everybody's searching, all the, Google server goes crazy. All of a sudden, you may want a couple more megawatts to power those important searches people are doing, right? And they can't raise the power consumption. What they do instead is not take it from the grid, but take it from the batteries, right? So they actually use the batteries to smooth out those peaks as well. And this was another reason they had these batteries more than they probably needed for other reasons, for the battery backup reason. They could actually charge these at off-peak and run them at peak from the battery to stop pulling from the grid, all right? So, at this scale, when you're dealing with, tens of megawatts of power consumption, that power engineering is a big factor in data center design. So now we've dived down to the single board level. How do we program at the single board level? Well, you saw that in the earlier project, in Project 3, using OpenMP. So now you can parallelize across the few cores that you have on each of those motherboards. And again, we're using abstraction. Here we write a for loop, then a little pragma actually tells the system how to break it up and parallelize it across so you didn't have to go in there and do a lot of heavy lifting in terms of parallelizing your code yourself. It's just a few pragmas you added. Though, as we'll see in the competition results, some people do go in there and do a lot of work making things go real faster. So this kind of board level, how we're using more transistors. Well, we have multi-core, multiple processors on each chip, and we're also adding these extra things like the SIMD units, the vector units. We're also using cache memories in the design of those boards, this memory hierarchy idea. And across those cores, using thread-level parallelism and also SIMD parallelism at the vector unit level. Let's peer inside the processor. So these guys picked a AMD Opteron. Like I said, this was a cost-performance decision by these guys. So here's a chip on a board. This is something about this big, for those of you who've never opened up a computer. If you haven't opened a computer, go home and open up your computer. Just take a look inside, right? You should know what the inside of a computer looks like. And the AMD Opteron is an interesting architecture. So it's x86 architecture. So here's the whole pipeline of the Opteron. So at the top, there's an instruction cache. We learned about that, how a lot of code, hot working loops can fit in a relatively small instruction cache. You're not going to add to memory. It reads from the cache. It does decodes those instructions and then executes them. Now, the interesting thing about the x86 has a very complex instruction set. The MIPS you learned was very simple. The x86 was designed a long time ago in a different era and has many, many complicated instructions. Instructions that, for example, will copy a whole string in one instruction. They'll do a struct copy in a single instruction in the x86. And so the way the guys designed this is to actually take those complicated instructions and break them down into those little RISC things. So on the fly, the hardware is taking the x86 instructions and converting them to little RISC-like instructions. And those RISC instructions will actually get executed inside the core of this processor, right? And so it has multiple different execution units, integer units, floating point adder, floating point multiplier, other stuff. These are where the vector units live, the SSE extensions. Load store pipe talks to the data cache, and it can execute multiple of these RISC ops per cycle. So 5 or 6 or so of these RISC operations can execute on the same clock cycle inside the machine. And what's more exciting is they can do those out of order. So you're reading the program in one order from the instruction cache. You're figuring out on the fly how to reorder those, breaking them into micro-ops, and figuring out on the fly how to reorder those micro-ops to try and keep everything busy. And all this is being done in hardware on the fly inside the machine. That's happening in here. And what's more is doing this thing called register renaming, where you think you're writing register 3, but in fact the machine is writing to some other register. You could have multiple instructions that all think they're writing to register 3. They're actually writing to different places inside the machine. To learn how about all that works, you should take 152. But that's at the core of this machine. And then at the bottom is a commit unit that kind of puts all the pieces back together again. So it looks to the program as if you just executed one instruction at a time. Okay. So the Opteron has this big pipeline. You learn about pipelining. In this case, it's pretty long. There's 12 stages in the pipeline, not just 5. There's 12 stages here. And floating point operations, 17 stages in the pipeline, from when you fetch it from the instruction cache to when you retire the instruction, having completed it. And at any one time, even though the pipeline seems quite long, 17 stages long, it's also wide. And you can actually have up to 106 operations partially executed in the machine at the same time. So there's 100 things in flight at the same time. And like I said, these can be executing out of order from each other inside the machine. And all this is inside one core. That's one of many cores on one chip. That's one of the chips on a motherboard. That's one of the nodes in a rack. That's one of the racks in a container. That's one of the containers in a data center, right? So remember, you have something like order of 100,000 of these computers inside a data center. And each one of these computers has multiple chips and multiple cores on it. And each of these cores has this level of complexity, right? And what it's doing. So I'm going to skip through this. This is just a picture of the die photo. Now we're looking at something that's about a centimeter or so on a side. 1 or 2 centimeters on a side. And here you see here's the 2 cores in this case. You can see the instruction fetch unit, the load store unit. This is the instruction cache. This is the data cache. These are level 1 caches. And here's the level 2 cache. And there's 2 megabytes total of level 2 cache. Here's 1 megabyte. Here's another megabyte. So you see the core, that very big, complicated core, is about as big as 1 megabyte of memory on the chip, right? That's about how big each core is. Okay, so let's keep going down. Here's one of the cores. We're sort of millimeter scale here. These are a few millimeters on a side. Here's the floating point unit. Here's the load store unit, instruction fetch. Here's the iCache. So basically instructions flow from the instruction cache into the instruction fetch unit, into the execution units. Load store unit touches the data cache, and instructions go to the floating point unit, right? So when you're programming one core, you're sort of down at the C level, and we showed you how to use these intrinsics to target the SSE and AVX extensions inside these Intel processors, right? So this C code here is what's driving that parallel vector unit, these intrinsics. We could have told you how to access that there. Going down, once the compiler's got at it, you end up with this, compiled assembly code. That's really the assembly code is the last step. There's machine code, then you get into the hardware. That's really the interface between software and hardware, is this assembly code, machine code. This is what the hardware actually understands down at the lowest level, right? And you wouldn't really want to be writing this stuff by hand if you could help it. Right? So, down at the core level, this idea of abstraction, we write, in this example, we're writing x86 assembly code that gets turned into machine code. And that's the interface between software and hardware. However, as we saw in this chip, the story doesn't really end there because the hardware takes that x86 assembly code and actually turns it into something else internally. So inside the chip, it's breaking it up into something that looks like those RISC instructions you've been using in MIPS. Executes those, but completes them and commits them so it looks like it did those x86 instructions on the outside. So that's the idea of abstraction. We hide the fact that all this stuff is going on and make it look like an x86 on the outside because that's what all the software expects on the outside. And we saw inside that core, there's a lot of parallelism. There's instructions happening in parallel, there's pipelining, things happening out of order, and in those vector units, you have stuff, this data level parallelism as well. So let's dive down even further. So if you go inside one of those vector units that's doing these SIMD instructions, you got 4 adders working at the same time. So at 128-bit instruction, you can do 4 32-bit adds, all operating in parallel, right? That's one instruction in one cycle can do these 4 operations, right? If you peer down even further inside one of those adders, right, you've got 32 bits coming in, you've got the adder here coming out, and each of those bits has multiple gates that work in parallel, right? So you have 32 bits working in parallel. Inside each of those bits of logic, you have multiple gates working in parallel, right? And you peer down even further, each of those gates is made out of transistors, right? And those transistors, like these, they're the fundamental units of hardware, these switches that, depending on whether the control gate is on or off, they conduct or don't conduct. And this is how we build logic gates, right? So right down at the lowest level, we have these transistors. Let's go down one level more than we actually covered in class. So this is the schematic level view. These are what the components look like conceptually. But what happens when you turn them into chips? What does it actually look like on the chip surface when you turn them into real devices? So this is kind of the layout of a single gate. And we're down here at the sort of 10, 100 nanometer range, so 100 nanometer scale design. So what this is showing you is looking down onto the surface of the chip, right? So looking down from above. And this blue stuff represents metal. So this is, these days, this would be copper, a copper trace. And these black dots represent connections down to the level below. So like what we call vias, where you go from one layer down. So the chips have multiple layers of stuff. Some of those layers are metal above the surface of the chip. And in the surface of the chip are the actual transistors. So the metal layers are used to wire everything together. And these days, like we mentioned in class, some of the chips have up to 17 levels of metal of wiring to connect things together. We're only showing one level of metal here, this level at the bottom. You can see here, VD, this is the power line coming in and actually touching the transistor here. So this is connecting to the source of this transistor here. So this is one transistor in the NAND gate. This is one transistor in the NAND gate. This is the other transistor. Here's the other two. So if you go back to the schematic, there's 2 pull-up transistors and there's 2 pull-down transistors. These are the 2 pull-up transistors here. So VDD on one side, and this is their common node here, comes out. These are the 2 pull-down transistors. These are connected in series. So this is ground here, contacted here, and this is the output of that's the output here, and this is the series connection here. This is the series connection. These are the 2 transistors. This stuff is the gate material, polysilicon. So, very detailed designers take that schematic and figure out how to pack it together. And this is like playing Tetris. You've got to figure out how to get all the connections and squeeze it into as little space as possible while making it legal to manufacture, right? You have to squeeze all these dimensions and pack it all in and get that functionality in something that's legal to manufacture but as small as possible. And they do other kinds of tricks to reduce the capacitances, like this trick about this node, which is here, between these 2 transistors. They actually sort of share that between these 2 guys at all the capacitance on this output node, right, to save power. So there's a lot of details in this physical design. There's expert designers who spend their lives looking at screens and packing this stuff very tightly. But what they do is they build these cells, like a NAND gate. And then other designers will use those cells in the libraries. So not everybody's designing these AND gates. Just a few experts design these, and everybody else uses them. And that's another example of abstraction. I guess it's actually giving you some, electron microscope looks at the, structures at the bottom. Here's the contacts, the metal coming in, contacting down onto these other layers. Notice how it's kind of fuzzy here. When we do this drawing here, everything's like a perfect rectangle, right? That's just abstractly what it's supposed to be. But these things are manufactured in industrial processes at the fab, and real life things get not perfectly produced. This is pretty good, pretty square, but notice how all the corners are rounded, and that's just the physical process of etching it and making these transistors makes it. This is a real world device. Not everything is perfect, but it's good enough. It's good enough that you can have billions of transistors on a single chip, all reliably connected. Right? That's pretty amazing to me, anyway, that you can do that these days. This is just looking in plan. If you cut through the chip, slice it the other way. We've been looking down at the top, but if you sort of turn it around at right angles and slice through it, you can now see the layers stacked up. And here's sort of layers of metal on a chip. So these are copper wires, different wiring layers. So diving down into memory, so we talked about memory a lot. You have a lot of bits in an array. A single bit of SRAM takes 6 transistors, and this is the schematic diagram of 1 bit of memory, right, with 6 transistors. And what this is are 2 sets of inverters back to back. So you have inverters feeding each other, and that's stable if they both agree on where's 0 and 1. There's 2 possible states of that. And you can flip it by using these 2 transistors, sending in a bit line a different value along these true and complement lines here, opening up both of these transistors and then flipping the cell. And when you read it, use the same 2 transistors. You open this up and read out the value on these 2 bit lines. Right, and that's the way the 6 transistor bit cell works. Right, so you need 6 transistors to make a static RAM. It holds the value as long as power is there. You don't need to do anything special to it. This is the layout of that SRAM bit, and there's experts who spend their careers designing SRAMs. This is like a very special niche, and in every process technology, as things scale down, things change around a little bit. And this is usually one of the most critical components in any new technology, because most of a chip is memory these days. Like all those caches, those huge memories. The L1 caches, the outer caches, the register files, they're all SRAM-like structures. And making those dense is really important to the cost. So people spend their lives optimizing away how these things get packed together. Right? And this is just looking at how it's laid out when it looks through cross-section, bits in an SRAM. Right? I think it was actually off an Apple chip. Somebody looked at what they were using in their SRAM technology. So looking at bits of the memory as well, DRAM is also very important. That's where most of our memory is these days. So one of the tricks people use now is double data rate. They transfer bits on the rising and falling edge of the clock, not just one edge of the clock, to go twice as fast. They have single error correcting, double error correcting codes. We talked about that last time. And also a chip kill thing where you only really need 7 bits to cover the 64 bits. By having the 8th bit, you can actually do this thing of detecting when all of the bits in one chip have failed, so you know that one chip has died. So that's another form of redundancy. Here's some stats here, like the server. I guess it's from a Google study. Over a year, they kind of see about 20,000 correctable errors on a server. It doesn't sound like that many over a year, but if they were uncorrected, that'd be pretty bad. And they get about 1 uncorrectable error per year. Now, not every uncorrectable error is terrible, because a lot of times error happens in stuff you don't care about. Like you weren't going to read that data anyway. What you really worry about when there was an uncorrectable error you didn't know about, and it corrupted something important, right? And that's much less frequent. So DRAM is this very, very dense memory. We're sort of this is an array of DRAM bits. There's just 1 transistor and 1 capacitor on each DRAM cell. So the transistor gives you access. When it's on, you can charge and discharge this capacitor, so you can write a value to it or find out how much charge there is there to read the value. Because it's a capacitor and it's in this process, the charge actually leaks away over time. So you have to keep refreshing it. You have to occasionally go back, read the value, and rewrite the value back again to kind of top it back up again. Was it a 0? If it's a 0, I'll really make sure it's a 0. Was it a 1? I'll write the 1 back again. That's why it's called dynamic RAM. You're continually reading it and refreshing it. The layout of these things is probably not obvious how it gets from there to here, but it's just a couple of lines with the capacitor hidden under. This is actually the access transistor here, and this is the metal word line. This is the access transistor. This is the bit line that the charge is going to be read out and written from. And this is the storage cell. So very dense. And if you look at this in cross-section, yep.
How often does DRAM refresh itself?
How often does these days, the question was how often does DRAM refresh itself? It doesn't refresh itself usually. Usually the controller tells it to refresh, but you usually have to hit every bit every 64 milliseconds is the industry standard. So every tenth of a second, or well, a bit more frequently than that, you have to go back and refresh every bit. It turns out that depends on the temperature, and it takes a lot of power to refresh it like that. So in mobile phones, you actually have a temperature sensor. So they know how hot it is. The hotter it is, the more leakage there is, because the electrons have more energy, they can move more easily. And so on your phones, it'll actually have a temperature sensor telling the system how often it needs to refresh. And the idea is when your phone is cold, it doesn't have to refresh as often, and so they can save power. And when it's hot or it's in your pocket, it's actually going to refresh more often, right? So it'll take more power. So this is looking at how you fabricate DRAM. Those capacitors were the charges stored. And as we shrunk things down in 2 dimensions, made things smaller and smaller and smaller, they wanted to keep the charge about the same, so they had to kind of grow in the other dimensions. These are like 3-dimensional structures. And one way of doing it is you dig down into the wafer and build this trench, right? So here's a trench built into the silicon, and this is where the capacitor is. So between here and here are the 2 plates of the capacitor, and that's actually where the memory bit is stored, is the charge on that capacitor buried into the silicon wafer. So we talked about a bunch of this already. We have error protection on these things. The whole memory hierarchy, the L1 cache, the L2 cache, DRAM, it's all protected with these codes because that's where you're going to get errors. Memory is very dense and susceptible to all these errors. The other thing I mentioned last time as well, these guys have autonomous background hardware scrubbers. So you're basically reading, as you're refreshing it, did I refresh it and find an error? If I saw, I'm going to clean it up and write it back again without the error, right? So you're continuously getting rid of those single-bit errors. And the reason to do that is you can't correct a double-bit error, so you want to try and get rid of all the single-bit ones so you don't get the double-bit ones, right? So jumping back up to programming, we know we're going to have a memory hierarchy, so how are you going to make use of it, get the best performance out of it? You could do nothing and just rely on, it's probably okay. Caches take advantage of what programmers usually write, but if you really want to get the best performance, you really have to code knowing there's a cache hierarchy. So we talked to you about cache tiling, and in the project you looked at this, how to use blocking to actually get high performance by making the system reuse things more. So some of the great ideas here, the hierarchy, dependability again, and using that Moore's law for bigger capacity. Okay, so that was kind of a lightning, just everything you've covered, like biggest systems all the way down to individual logic gates and bits in the memory. So we covered a lot in this class. As well as all that, we covered how to program it. So it should have felt like a whirlwind tour because it was. There's a lot more depth to cover all these features. But remember, a lot of it's about the hardware-software interface. What's the hardware you're building? How are you going to program it? And what are the important things there? And one thing is interviewers will ask you, definitely looking for jobs in this area, anything in systems. They want to know what you did this semester. So hopefully you can tell them that, we built a CPU from Gates, right? I could run software. We wrote an assembler. We programmed a warehouse-scale computer to do, to find cats, right? That was, what you did this semester, right? So you'll be able to, great response to all those interview questions. They'll be, oh, great, you're the perfect high-performance cat finder that we've just been looking for our new job. Okay, so diving into Administrivia. So really, end of the class, all that's left is the final. So like last final of the last day of finals week. It's going to be in here. You can use 3 cheat sheets, both sides. So, you can save the ones you use for midterm 1, midterm 2. You'll need those again because we'll be doing that material as well as the post-midterm 2 stuff, just in case you're unclear about clobbering. So the final can clobber your scores in midterm 1 and midterm 2. Midterm 1 and midterm 2 cannot clobber those sections in the final. You have to do all of the final, right? If you don't, you will not get any points there. It only works the other way around. It's only a one-way trip. The idea is when you did the midterm, you may not have realized you didn't know the material. After you got your grade back, you may have learned some more stuff. So it goes that way around. It doesn't work the other way around. You have to do all the sections in the final. Don't rely on your midterm 1 and midterm 2 grade to clobber forward. It doesn't work that way. Okay, there's going to be review sessions. The TAs, May the 6th. HKN, May the 4th. May the 4th be with you. There'll be a Gorilla section being planned, so stay tuned for that. Okay, now the fun part of the lecture. So we had this competition, and so let me, you all saw the project. You know what the competition was, finding cats, right? Oh, So let me switch to the other prize deck. So now you'll be waiting to find out who the winners were. So when we set out the challenge was, we want you to try and get to 5 kilocats per second, right? That was our threshold of excellence, right? Try and get to 5 kilocats per second. So apparently we got this just about right because 4 teams, out of all you guys, 4 teams achieved this goal, right? So 4 people got above the 5 kilocats per second boundary. So we'd like to honor those 4 teams. So, honorable mention, 4th place, 5,123 cats per second. Can you tang, John? Your tang. Come on down. If you're in here, come on down. They're not here. Are they here? Are you here? Yep, come on down. So, you get these prize certificates of achievement.
Thank you.
So, photo time. Okay. All right. Photo the certificates. All right. So, in 3rd place, bronze medal, 5,939 cats per second. So, this was Edward Look, Maximilian Land. You guys here? Come on down. Are they here? No, they're not here? Oh, they're hiding. Oh, they're not here. Okay, we'll give them another round anyway. Okay, silver medal, 7,316 cats per second. Right? That's pretty impressive. Xu Heng Dai and Zhuao Lo, come on. You guys here? They're not here. Oh, there they are. Come on down. Come on. All right. So I guess your partner's not here?
I guess not.
Okay. Which one are you? Okay. All right. We'll take a photo. There you go. Great job. So now we thought that was a pretty amazing 7,000. That was almost 50% more cats than we thought people would hit this semester. But in first place, it's quite amazing. We were very amazed to find 16,500 cats. That's a lot of cats. So, Harry Hain, Jason Su, come on now. So now this was a stunning achievement. I think the TAs went and checked the code. Let's take a photo. Okay, you guys, the winning guys. So, oh no, you want to show them? Right. So now this deserves special recognition. This is beyond, way above and beyond. So we decided the TAs decided have to give them a special prize. So these guys have 2 grumpy cats. So, photo. So these guys. All right. Okay. So, and we thought it might be good if you guys could just explain what you did. How did you get this many cats per second? You can just hold it.
Okay. Okay. So what I did is just majority is the register optimization. So first it's the function specialization. So I replace many, so some variable can be constants in some layer. So just replace those variables to constants so you can save some registers. So for example, if you have 16 registers total, if you just save some register, maybe you don't need don't need to read caches. And moreover, there are 16 YMM registers. So I use all of them. So maybe optimize it. I don't know how to explain, but and besides, I use the AVX2 instruction. So the makefile doesn't have AVX2 flag, so you can't use normal way to use that. But I write the x86 assembly code inside the C source file, so I use it. There's some performance boost. Yeah.
Thank you. Do you want to say something? Okay. Oh, very good job. Yeah. So amazing job, right? I guess. So, yeah, we did find a few people who were playing with the timing function. That wasn't a good way to try and improve the performance. So not really recommended if you want a good reference letter for grad school. No. Okay. So that was amazing performance on the. We never thought anybody get above 10K. Never mind 16K. But diving into the instruction set manuals, reading what's actually inside the processor and making use of it is kind of the key to success, I guess. All right, so just to make you realize that this area of these convolutional neural network is so hot that Google is buying startups at an incredible rate who can make things like this happen. So you guys, you should talk to my buddies at Google and see how much they'll give you for your code. Oh, okay, let's just switch back. So just to finish up, I wanted to talk about what's next. So you're pretty much done with 61C. Some of you may still like this stuff. If you really like the digital system design, I recommend you take CS 150, and that's been offered in the fall. So CS 150 is you get to play with logic design mapping into an FPGA, a programmable logic array, to actually see your design running in real hardware. And you get to build a simple processor and extend it with some specialized engine. They've done graphics and things in the past. I'm not sure what's going to be in the fall's course. But that's, you read deep into digital system design. It is a heavy class. It's a 5-unit class. But most of the people who take it really enjoy it because you actually get to see your design running. It's a really fun project if you like hardware design. If you like computer architecture and you want to understand how an out-of-order processor works and how branch predictors work and what's this VLIW stuff and what's inside all these processors. You take CS 152, that's offered in the spring, so I'll be teaching that in the spring. And you'll really learn all the tricks that go on inside these microprocessors in there, and also a bit of the history of where all these ideas came from. And then another venture, if you're interested in all the operating system stuff, virtual memory and low-level systems programming, you should take CS 162, which will get you that next level of software just above the hardware. And how that works, right? And I'd say all these classes go together. Well, if you're interested in computer architecture in general, you should take these 3 upper div classes, at least these 3, as well as a bunch of the other ones. You guys are going to go out and do great things. You're Cal alumni. So one thing about Cal alumni in the future is, well, in CS, there's a lot of opportunities. One of the reasons our classes have got so big is suddenly everybody on campus has realized CS is the future, right? And, whether you're doing stats in CS, doing that kind of machine learning we had in the project to find cats, we're doing something like finding cancer genes, almost the same, cats, cancer genes, same thing, same algorithms. That's also important. Lots of things, even people doing computational journalism, like looking for trends in, gather 100,000 news reports, look what the trends in there. So CS is affecting all these different areas across campus. And so as CS experts, you'll be wanted, whatever field you're in, the CS people will be the most highly paid in that field. People understand computer science. I guess you guys are smart enough to figure that out. That's why you're in this class. The thing about being a cow, you know, you guys work hard, you know you can do stuff, can-do attitude, right? You never give up. You know, we're not the most well-funded school, shall we say, but we're the best. And the best way to predict the future is to invent it. This is an old saying from Alan Kay. You guys are going to be inventing the next system, so in 10 years' time, I'll be talking about your stuff here in 61C. Anyway, future's up to you. So thanks a lot. It's been a fun semester. Good luck on the final. Oh, yeah. Big thanks to all the staff. Stand up.
I have some announcement.
Okay. Dong Yi has one announcement.
Okay, so how many of you guys finished running on EC2? Not yet? Okay, I know some of you already finished it, right? And then I hope that you have enough time, so you have 7 hours for 5 instances, and 5 hours for 10 instances, right? It's enough. And if you didn't meet any performance guideline on test, right? Then you shouldn't run, your code on launch small or launch large, okay? So if you cannot meet your performance guideline, then I will have, extra office hour during Friday to Sunday, okay? So you can visit my office hour to save money, okay? I need your help, okay? Okay, thank you guys.
Thank you. Thanks, sir. Yeah, so this is all going on Dong Yu's personal credit card, so he's very worried about how much. Okay, thanks, everybody. Goodbye.